Okay, so now it's time to talk about relativity. So far we have introduced what is gravitational force, what is gravitational field, what is gravitational energy, and then how to calculate the orbits of objects using those forces. It's a lie. So everything I've said so far is basically a lie. Now, if you had lived before 1905, though, everything was great. So Sir Isaac Newton comes up with all of these theories as to what is gravitational force, and then energy, and then the field, and then plotting the orbits, and it worked perfectly well, okay? And so nobody really had a complaint about it until a guy by the name of Albert Einstein comes on the scene. And so you can see that he was born in 1879 and was lived until 1955. And he has a pretty hard life, okay? So when he was like in high school, his math teachers didn't really think a whole lot of him because he had a completely different way of viewing how things operated. And so they thought that he would never amount to anything. So what he did was he actually went to college and he failed. So when he went the first time, he wasn't able to do much. So he got a job in a patent office and he started reading books. So if he didn't know anything about calculus, he went to the library and he got a book on calculus. If he didn't know something about physics, he went to the library, he got a book on physics. So he basically taught himself everything about physics and mathematics. It was also a good thing that he married a mathematician. So his wife had a doctorate in mathematics. So it's been thought that a lot, even though Albert Einstein might have come up with the theories of relativity, it was probably his wife that did a lot of the calculations for him. So we don't know that for sure, but it was probably very helpful that he had a mathematician for a wife. Okay, so let's get back to the theory of special relativity, 1905. So the theory of special relativity is to explain how space, okay, now what do we mean by space? Up, down, sideways, in, out. So 3 dimensions of space and then 1 dimension of time. Okay, and then how does space and time and mass and energy change in a frame of reference that is moving at a constant speed relative to another frame of reference? So what do I mean? So let's say the Earth is 1 frame of reference. And then you got Albert Einstein in his rocket ship flying past the Earth. He would be in another frame of reference moving relative to the Earth. So that's why we call it relativity. Well, one of the things that he came up with was the idea of space-time. So he said that we don't live in 3 dimensions. We live in 4 dimensions. So the 3 dimensions of space added to the dimension of time, so that all 4 of those concepts are intertwined with each other. So you can't change space without changing time, and vice versa. So here's some of the really weird things that happen according to the special theory of relativity. So pretend that you're Albert Einstein, you're in your rocket ship. You have a ruler, okay? You look at the ruler, it's a perfectly normal looking ruler. Now you're going to fly past the Earth going at a very high rate of speed, close to the speed of light. And then as you pass the Earth, you're going to take your ruler and put it out the porthole, and you're going to compare your ruler with a ruler that is on the Earth. And what you're going to see is that ruler on the Earth has gotten smaller. It has shrunk. Okay, so it has contracted. And it's not just the ruler. So it's actually the entire planet. So the entire planet has gotten thinner. It didn't change this way, but it changed this way as you flew past it. So lengths contract. Then he looks at his watch, and it's perfectly normal. But he looks at a watch on the Earth, and he would notice it's running slower. And then he would look at his own mass in the rocket ship, and it's normal. And then he looks at the same mass on Earth, and it got bigger. So it got heavier. So all of these different shifts can be proven just by using algebra. So the special theory of relativity is not that difficult to understand. So you could find that on the internet, and you would learn all about how to calculate how much a ruler will contract or a watch will slow down. Well, for most people, this would be a major accomplishment, coming up with this idea. But that's not enough for Albert Einstein. So Albert Einstein then wanted to know what would happen in an accelerating system. So in special theory, it is a system that's moving at a constant speed, which means no acceleration. And now he wanted to expand it to an accelerating reference system. Do you remember that when we take an object and we drop it, it accelerates because of gravity? So this theory will include the effects of gravity. And in order to do this, he found also that measurements of length and time and energy, so all of the things that we normally think of as unchanging will change in an accelerating system. And in order to do this, he came up with 10 equations that would relate the mass of an object to how it bends space and time. So in that first picture over there, it shows what does an object do if there is no mass present. Do you notice it goes in a straight line? Well, Sir Isaac Newton would say, see, an object goes in a straight line unless there's a force acting on it. So that is Newton's first law. But the question is, what happens if there's a mass? Now, you can do this at home. So on your bed, make sure it's completely flat. Take a tennis ball, roll it across your bed. It goes in a straight line. All right, now take a big, heavy bowling ball and put it in the middle of your bed. Look at what the covers do. Do you see that the covers do this? So they're going to bend around the bowling ball. So the bowling ball represents a very massive object like a star. And it is going to bend not only space, but it bends time as well. And so if you take that tennis ball and you roll it on your bed, it's going to alter its course because it feels how those covers have bent underneath the bowling ball. So this is the correct way of viewing motion. So Sir Isaac Newton's idea of force of gravity equals m1, m2, it's a good approximation for how the force of gravity works, but it's not the correct one. So the correct one is by using this general theory of relativity. Now, for most things, though, the regular way of viewing how nature works using Newton's laws is perfectly okay. It's just when you get near very large objects, or if you're traveling at close to the speed of light, that you really need to use these special ways of looking at the universe. So I thought that you might be interested in looking at Einstein's field equations. So up there at the top is the actual field equations, and then underneath it is what happens when you expand them into the 10 pieces. So if you look, you got 10 pieces on the left-hand side, and then on the right-hand side you've got those other 2 pieces. And so the left-hand side of the equation is going to be related to the amount of curvature of space and time. And then on the right-hand side is what is causing the curvature. Now, so far, we only said that mass bends space and time. But you notice that there's 2 pieces there. And the piece that is this one, so this is going to be called the cosmological constant. And in astronomy, we are finding that the universe is expanding. It's getting larger at an ever faster rate. So the galaxies are moving away from the Earth. And so our explanation for that is going to be called dark energy. And dark energy is going to be related to this cosmological constant. You can almost think of this thing as being anti-gravity, but it's an expansion of space and time, and it's the second part to Einstein's field equations. Another interesting thing is what happens if you take general relativity to its extreme. So there's these things, stars, if they're very, very massive, when they start to die, they implode. So the gravity pulls this dying star in on itself. And if the star is too big, it will explode. But even that explosion is not enough to keep the core from continuing to collapse. And so it's going to turn into this thing called a black hole. So the object ceases to exist. It has no physical dimensions. It has no length, no width, no height, but it still has all of its mass. And so we're going to call this thing a black hole. And in the case of this represented flat space-time, and then when you put the bowling ball on there, then you got this. So that is curved space-time caused by a star. So what would a black hole be? Well, a black hole would be a rupture in space and time. So it would come down to this infinitesimal point right here. And if you were a person falling into the black hole, it would not be a pleasant experience, because your feet, let's say you're falling feet first into the black hole, your feet would be closer to the black hole than your head. So that means your feet would be experiencing more gravity, which means that your body would be stretched out until finally, by the time that you enter the black hole, you're nothing but a stream of subatomic particles going down the black hole. Now, there are some people that say that black holes, the material that goes into it, then goes into a wormhole. And then the wormhole connects this black hole to some other place in the universe where the material comes spraying out, and then that would be a white hole. But there's no evidence for white holes. But that doesn't stop science fiction writers. Okay, let's take a break, and when we come back, it's bonus time.